Inicia la grabación. Perfecto. Muy bien. A todos los participantes, a los estudiantes, a los profesores y a los invitados externos, gracias por estar hoy presente en la segunda que tenemos hoy en nuestro ciclo de videoconferencias en logística. Y en el día de hoy tenemos entonces un invitado que nos hablará del tema de cómo los ingenieros industriales y logísticos pueden optimizar la logística industrial mediante el uso de analítica avanzada. Deseo recordarles a todos cómo va a funcionar la metodología de la conferencia. Primero tenemos una presentación magistral del expositor y al final tenemos la sesión de preguntas y respuestas. En caso de usted tener preguntas, por favor colocarlas en el chat de la videoconferencia aquí en Teams y yo se las estaré leyendo al expositor. En caso de colocarla, puede colocarla también en español o en inglés. Si la coloca en español no hay problema, se traduce y se la pregunto al expositor. Así que no los limite el idioma. Y también quería recordarles y pedirles amablemente apagar sus micrófonos y apagar sus cámaras. En el caso de que alguien entre y bueno, tenga su micrófono encendido y no se dio cuenta, le voy a pedir el favor a Caitlin que por favor les apague el micrófono, si podrías estar pendiente de eso. Y bueno, comenzaremos entonces ahorita con la presentación. Good morning, ladies and gentlemen. Welcome to our second presentation, which is part of our conferences in production in logistics. It is a great pleasure for me to introduce today our speaker, who's going to talk to us about how industrial and logistics engineers can optimize with advanced analytics. A brief reminder before we start, I will to kind of off your mics and your camera impression Q&A session. If you may have any questions, please write them down on the chat of this video call and I will read them out loud to our guest speaker. So, ladies and gentlemen, please join me in welcoming Lennart Felkel. Lennart, jetzt kannst du anfangen.
Okay. Yeah, thank you very much. I prepared a presentation for this event. I'm going to share my screen. Thank you very much for letting me participate. So my name is Lennart Felkel, and I hope you can all see my screen. Otherwise, please let me know. And I'm an industrial engineer, so I studied industrial engineering at the university in Germany called Karlsruhe Institute of Technology, and later did my master's in management, economics, and technology at the Swiss Federal Institute of Technology in Zurich, and studied a mixture of computer science, manufacturing, and operations management. Since I graduated in 2017, I worked for a German automotive industry in the area of logistics, as well as I worked in the German heavy load logistics manufacturing industry, which is now also active in container terminal industry, which I will introduce later. And I also run a blog called Supply Chain Data Analytics, where I try to promote the application of advanced analytics to supply chain management and manufacturing systems. And I wanted to provide some motivation in this presentation for getting into the field of advanced analytics, for having an impact on supply chain management and operation management, especially interesting, in my opinion, for industrial engineers, logistics engineers, and manufacturing engineers. And so advanced analytics in itself is, in my opinion, a term that is not clearly defined and has yet to be clearly defined. In my opinion, I would attribute the following areas to the field of advanced analytics. So certainly visualization in various forms, for example, map-based spatial data visualization, but also data plotting and conventional data visualization is for me an area of analytics or advanced analytics. Then time series analysis, so an area dedicated to the analysis of historical time series data, for example, historical sales data, but also development of forecasting models for time series, as for example, forecasting models for sales development. Semantic analysis is for me also an area of advanced analytics. Sentiment analysis, especially sentiment analysis related to online trace data, for example, sentiment analysis of Twitter data, Facebook data, news-related data. So analysis of text to derive sentiment from text published on the internet. Certainly a very interesting area which I would attribute to advanced analytics, and which also has applications in the area of supply chain management and operations management. Network analysis, network optimization, network design. So optimization of supply chain networks to improve lead times, stock levels, overall logistic costs. Definitely an area where advanced analytics can be applied, such as, for example, mixed integer programming, linear programming. I think a very interesting area for industrial engineers and logistics engineers where advanced analytics can be applied. Cluster analysis, descriptive statistics, also areas that I would attribute to advanced analytics. And then my main field, discrete event simulation, which I also currently work in, is definitely also an area that I would attribute to advanced analytics, and where there are a lot of applications in manufacturing and supply chain management. And discrete event simulation is basically about developing models that describe a system as a chain of discrete events. So, for example, manufacturing systems, logistics systems are systems that can be described with a discrete event simulation. And here you have the possibility to develop simulation models of systems in order to optimize the performance of the systems or reduce the costs. And it is especially applied when conventional methods, like, for example, deterministic methods, static calculations, conventional methodology is not applicable, or if a system is too complex to be analyzed with conventional methods. Then another interesting area for me is agent-based simulation, so also simulation modeling, but in this case you model a system as a system comprised of agents, and then you study the emergence of system behavior from the individual interactions of the agents on the microscopic level of the system. This is an simulation modeling technology that then can be used in various areas of supply chain management, and also, for example, when modeling an economy of an entire country. System dynamics, also an area that basically is about developing simulation models, but again, a different methodology for developing simulation models, but also a methodology that can be used for describing supply chains. And this is basically a modeling approach that describes a system with stocks and flows and variables, and thereby it tries to capture the change in the system over time. Complex event processing, neural networks, also an area within advanced analytics where there are some applications within supply chain management. And then regression analysis, still a very important area. Linear optimization, so the development of optimization, mathematical optimization models to, for example, improve network designs, as described above here. Nonlinear optimization, so the development of mathematical optimization models with, for example, nonlinear objective functions, also an area that can be found within the area of advanced analytics in supply chain management. And then spatial data analysis, for example, heat mapping of customer sales data, scheduling algorithms, for example, staff scheduling, production scheduling, definitely also an area within advanced analytics. Pattern matching, data mining, test mining, semantic analysis, which I already mentioned up here, also all areas within advanced analytics. Supervised and unsupervised machine learning, as well as semi-supervised machine learning, are also areas where there's a lot of focus on right now within the area of advanced analytics. And basically, analytics methodology in itself, I think is normally classified into descriptive, predictive, and prescriptive analytics. I would add diagnostic analytics too, which in my opinion describes various degrees of maturity for analytics applied to, for example, operations management. And for example, descriptive analytics would be to derive information from historical data. So apply descriptive statistics, for example, to historical data to describe what happened in the past and to understand what happened in the past or what's presently happening. Diagnostic analytics is then an area of analytics where you try to understand the reasons behind the occurrence of certain events and observations. So you're no longer not only interested in catching what's currently going on, but you try to understand why things are going on, and you try to find the main drivers behind the trends and developments that are ongoing. Predictive analytics is then, for example, an area where models are trained on data, where you try to deliver predictions and where you try to, for example, predict what's going to happen in the future. So you try to use the information that you learned from the past and that you learned from your diagnostic analytics approach to then build models and concepts for predicting the future. And prescriptive analytics is then when you go one step further, in my opinion, and you develop analytics applications that in this stage no longer only form predictions, but that also recommend concrete actions that you can undertake to, for example, prevent risks or to improve a certain outcome. An example of descriptive analytics, or several examples for descriptive analytics, would be, for example, plotting sales data or capturing sales data. So reporting of current sales, reporting of current stocks, or displaying current backlogs, so reporting of the current backlog situation in a company. All areas that I would attribute to descriptive analytics. Also, for example, if you think of a factory, then reporting of plant-wise operational overall equipment effectiveness, and KPI indicating the effectiveness of your equipment. Certainly measuring this data would also be attributed to descriptive analytics. Or, for example, measuring the response rate of certain marketing campaigns or sales campaigns to see how many ads turn into sales. That will also be the measurement of this response rate would certainly also be what I would refer to as descriptive analytics. And if you then go one step further, we would then be talking about diagnostic analytics. So here you try to understand why things are happening. So, for example, you would no longer be interested in just capturing the picture of what's currently going on with sales, but now you want to understand why sales, for example, are going down in a certain area. Or you want to understand what caused the backlog in your system or in your supply chain. Or you want to understand why your OEE is below target and why you're performing poorly. Or if we go to the marketing campaigns, you want to understand why the response rate has dropped for a certain marketing campaign. So here you want to understand the main drivers behind trends that are going on. And predictive analytics, here you go one step further. So you try to learn from the previous two approaches. And now you, for example, want to predict which region is going to experience the fastest sales growth, or what supply chain disruptions are at risk of occurring. or what is the main risk right now for your OEE to go down. So you try to predict what might be potential causes that might hurt your overall equipment effectiveness. And in the same way, when talking about, for example, marketing campaigns or sales campaigns, you could now try to predict which customers or which particular customer is currently at high risk of defecting. So, for example, leaving your program or leaving your business and no longer being a customer. And then you could, for example, decide to target those customers that are at a high risk of defecting. And with prescriptive analytics, you now not only try to form predictions, but you try to really use analytics to provide options for decision makers to really make a decision and to implement some kind of change. So, for example, prescriptive analyst or prescriptive analytics approach might then recommend what product should be sold in a certain market. So where should you be putting your emphasis? Or a production schedule, an optimal production schedule would also be, in my opinion, attributed to prescriptive analytics. Or if you think about predictive maintenance and the Internet of Things and Industry 4.0, then in this case, machines would now be deciding when to do maintenance in order to optimize the overall equipment effectiveness. And in terms of marketing campaigns, if we go back to that example, then here prescriptive analytics might, for example, deliver options for which kind of campaigns you should promote to increase your response rate and to increase leads and sales. So those are the 4 areas of analytics and some examples provided to that. And currently there's a lot of focus on machine learning, artificial intelligence, especially in the area of data science. And one approach that I would maybe take is to focus on the, I would say, basics first, or try to first establish a good understanding of what's currently going on in your system. So focus on establishing some kind of descriptive analytics framework to really capture in a very transparent way what's currently going on in your supply chain and in your business. And then you can go on to a diagnostic analytics. So here you might be applying exploratory analysis methodology to understand what are the root causes for certain problems in your business. So what are the main levers that you have to address to optimize your results. This would be then diagnostic analytics. And then you could move on to predictive analytics, where you, for example, try to predict where you would be in the future, or you could, for example, predict potential risks that might occur in the future. And with prescriptive analytics, you would then move even one step further, and you would decide or deliver decisions or options for decisions on how to effectively change your business and your strategy, and, for example, your supply chain network based on analytics. Then here also to introduce the area of analytics, an overview of some important programming languages, in my opinion. So advanced analytics is definitely an area where coding and programming is of great use. And if you're good at programming, good at coding, then you will definitely have an advantage in this area. Besides a good mathematical foundation, a good understanding of mathematical models for example, optimization or forecasting, or whatever area you might then be working within. And one important programming language currently is certainly Python, which is an interpreted high-level general-purpose programming language. And it is currently especially popular for machine learning and in the area of data science. It's an open source language, and there are a lot of modules that are available for Python that can be used for example, forecasting, but also, for example, linear optimization or nonlinear optimization. Then there's R, which is also a free programming language with a main focus on statistics, so statistical computing and graphics, so data visualization, and definitely a important programming language if you are very much into statistics. A language where there are a lot of modules available or packages, it's called for R, where people around the world have already put a lot of work into writing functions or writing algorithms that solve some kind of statistics problem, and that you can then easily use in your script to solve your problem that you're sitting with. Excel VBA, also, in my opinion, important in any business, because Excel is very important, and usually analytics is done in Excel in most businesses. And with Excel VBA, you then have the additional flexibility to do whatever you want with, for example, Excel, and therefore certainly a language that also is very helpful if you want to get into this area. GAMS was another example of a language that I wrote here, which is a mathematical modeling language. It's a high-level modeling language for developing optimization models. So you can use it to, for example, develop linear optimization models, integer optimization models, and also nonlinear optimization models. So it's also used in the area of economics. So not only supply chain management, but you can definitely also use it for modeling, for example, facility location problems, vehicle routing problems, transportation problems, scheduling problems, assignment problems. All these kinds of mathematical problems can be modeled and solved with this software. And JavaScript is definitely also an important language, but more in terms of if you want to work with something related to the World Wide Web, since it's a core technology behind the World Wide Web. And Java is definitely also an important language, especially because it it's very platform independent, and allows application developers to write code once and run it anywhere. So a very, very platform independent language, and has its performance, especially in this area. C++ is also widely used, for example, also in algorithm development. A good thing about C++ is that it's a very fast language, so it allows you to work object-oriented. Java is, for example, also object-oriented, which allows you to structure your problem or your model using an object-oriented approach. But in addition to that, C++ is also very fast and faster than many other programming language, object-oriented programming languages, and that is one of the benefits of C++. Then I also put SAP, ABAP, which is a programming language for SAP, and you can develop custom applications for SAP. SAP, at least in Germany, where I'm located, is a very important enterprise resource planning software in the area of manufacturing, and almost a lot of companies that are into manufacturing, they run their ERP systems with SAP, and if you want to make add-ons, or you want to make customizations to your ERP systems, or you want to develop tools that run on top of your ERP system, then, for example, you can do it with this programming language, and that's one of the reasons why I put it here. And then SQL or SQL is a language especially important for example, managing data in relational databases or for querying data, so for obtaining data from relational databases. And if you work with huge data sets and a lot of data, then this is definitely an important language, and probably the most important languages of all the languages listed here to learn. But you don't need to use programming. You can also use some basic tools, and with just some basic tool knowledge, but a good mathematical understanding and good mathematical foundations, you can also solve many problems in real world industry, I would say. Here I just put a screenshot of a simple example I did with Excel solver, and this is a solver that comes with Excel and that allows you to solve optimization problems. You can see here I have a simple mathematical optimization model where I have an objective function 3x1 plus 2x2, which is maximized. So my target is to maximize this objective function when the value is calculated in this cell. And the formula, which is basically 3x1 plus 2x2, references these two cells. These two cells are optimized by Excel solver, which I tell Excel solver in this area. And then my model has some constraints. So for example, x1 and x2 have to be bigger than 2, and 1x1 plus 2x2 has to be smaller or equal to 10. And those constraints are added to the solver here in the subject to constraints section. And you can add it with this add button. Then in this case, I use the GRG nonlinear solver. I should have used the simplex solver. So there are different solving methods that you can choose from in this section. And then you can click solve, and this problem is optimized for you. And Excel solver will adjust the values in these cells so that you get the maximum value subject to those constraints. And you will also get the constraint value that represent the optimum. So in this case, no coding required to develop a mathematical model and to solve a simple mathematical model, as you would also find it in production management or supply chain management. In general, I would separate 3 different areas from each other. I would say industrial engineers can have an impact on the design, the planning, and the operation of manufacturing and logistics systems with analytics and advanced analytics. And design would be the design and the conception of logistics systems and manufacturing systems, be it a supply chain, be it a factory, be it an assembly line or a machine. In this area, you can, for example, think of simulation-based layout process design or layout optimization for a factory using simulation mythology, which is an area of analytics. Or you could think of network optimization, so optimizing the location of warehouses in a network, or determining the optimal locations of sales stores, or determining the optimal distribution of warehouse capacity in a supply chain. This would also be a design topic related to logistics and supply chain management, in which you can use analytics to solve real-world problems. And I put here some softwares and tools that you could think of in this area, and that you might maybe be interested in learning if you, for example, want to get into the area of factory planning or network optimization. So AutoCAD, a drawing tool, and not really an analytics tool, but simply a drawing tool for drawing factories, but important maybe to master if you want to go into a factory simulation, just as a very basic tool. Then I put here some simulation tools, for example, AnyLogic, Simio, or some discrete event simulation tools. AnyLogic also supports agent-based simulation and system dynamics simulation, and also discrete event simulation. And Simio, I know, supports discrete event simulation. So discrete event simulation would, for example, be a simulation approach used for simulating a production process or processes in general, but also can be used for modeling an entire supply chain. And then I put here some other tools. For example, a Google OR Tools is a package made openly available by Google for solving some of the hardest mathematical problems, and some of those problems are also related to supply chain management, supply chain design. For example, network optimization problems can be solved with Google OR Tools. And Google OR Tools can be accessed with various programming languages. For example, you can access Google OR Tools using Python. And then planning, that would be the second important area where I would say you can have an impact with analytics. And here I can think of time series analysis would be one example. So forecasting sales, analyzing historical sales, analyzing maybe also the supply side or inventory, maybe also analyzing overall domestic product or data related to economy, maybe also analyzing trends in commodities. So, for example, maybe analyzing historical developments in oil prices, future development in oil prices. So this would be an area that I would attribute to planning. And that is also tightly connected with demand and supply planning in general. And here I put some software tools again that might be especially interesting for this area. One software here is SAP again, as you see, which is an important ERP for example, manufacturing industry. And you see also that I put here topics such as lot size optimization, job scheduling, vehicle routing, which I would attribute to planning. So, for example, assigning vehicles to routes that would be no longer in the design phase of a supply chain, but then in the planning stage of a supply chain. So more short term, but still maybe on a weekly or monthly level. And then on a daily level or a bi-daily level, or certainly a weekly level, would then be areas such as reporting, root cause analysis, process monitoring, anomaly detection, predictive maintenance. This would be some of the areas where industrial engineers could have an impact on operations of supply chains and factories. And also here, I put some software that might be the first things that you would want to look at if you want to get into this area. I then wanted to show some examples for the design stage that I was talking about, and the application of analytics for the design stage. In this case, I'm showing a video from my employer, which is Amova. Amova is a subsidiary of the SMS Group, which is a leading partner in the world of metals, and famous for example, steel rolling mills and steel plant design, but also a big player in aluminum industry, copper industry, and now also with Box Bay, which I'm going to introduce on a slide, on an upcoming slide, an engineering company that is active in the area of container industry and container terminals. And what you see here is a simulation model I developed for Amova, where I modeled a high bay storage system that stores coils. So you can see here in different colors, there are coils that are stored here in this high bay storage, and that high bay storage is operated by two so-called stacker cranes, and these stacker cranes have to interact in this aisle. And if you look here at the layout, you can see this high bay storage is connected to various processes. Yeah, so you have, for example, here the receival of raw material, in this case, raw coils. And you have here rolling mills connected here. You have an annealing process that is connected here. And then you also have a quenching area here. So you have certain production processes going on here. And then you have finishing lines that are connected to this high bay storage system here. And all of this is fully automatic. So there are no, there's no human labor involved in this process. And a system that is highly optimized can be nicely analyzed using simulation technology and using discrete event simulation technology. And in this case, the question was, how much throughput can we achieve in a system like this? And how should we arrange the areas and zones inside this high bay storage system so that the throughput is optimized? And what you can see here is that in the simulation model that I developed from scratch using Python programming, I separated this high bay storage system into different zones. And for example, in this zone, only coils that are finished. So this is finished product or semi-finished product with a very high maturity degree that has undergone processes mainly connected to this area. These finished or semi-finished products, they are stored in this area only. Raw coils, so the raw material, you could say, for this production process is stored only in the first section here of the high bay storage. And then in the middle you have red and yellow coils, which would be coils that are hot. So coils that, for example, have been undergoing, if I go back here, have been undergoing an annealing process here. So an annealing process means a lot of heat. So these coils they are heated, and when they come back to the high bay storage, they have to cool. And in a high bay storage like this, you can apply cooling systems that run through the columns of the high bay storage, and you have in certain columns you have cooling channels, and these cooling channels, they blow cold air onto the coils, and they thereby support the cooling process, and they allow for faster cooling. So therefore, you have certain areas where you want to put your hot coils in order to have very fast cooling processes. The yellow coils that I showed here on the side, those are also hot coils, but they are not coming from this annealing process. They are coming from the rolling mill here. So in a rolling mill, you put thick steel, for example, and you mill it, or you roll it down to thinner steel. In this case, I think we're talking about it's an aluminium process. So in this case, it's thick aluminium that's then rolled down to thinner aluminium, and during this process, heat is also generated, and the coils after this process might also have a high temperature, so might have been heated up by this process, and therefore also these coils coming back from the rolling process are stored here in these columns with the cooling channels. In addition to that, you have then other coils that are not hot, so they're just cold coils that are waiting here to be sent to the annealing process or the rolling process connected on both sides of the high bay storage system. And then you can also see there's a green coil here, and that might be a coil, so product from here that has to be sent to a finishing line here. And since these stacker cranes, they separate the aisle, so they try to share the aisle by nearly 50%. So this stacker crane tries to operate this section, and this stacker crane tries to operate this section. If something needs to go from here to, for example, here or here, then this stacker crane has to either move in here and send the stacker crane away, or it has to place the coil or product at a location where then the stacker crane is taking over the product. And in this case, I chose to model or design the system with a static handover location. So in this case, the stacker cranes, they hand over coils to one another through certain storage cells. And this is an example where, due to the interaction of the two stacker cranes, which is a dynamic and unpredictable interaction and complex interaction, you cannot use conventional calculations, and you cannot use a static calculation or a simple calculation approach to estimate the throughput of a system like this. And an example of a problem where you need simulation methodology to analyze the throughput that you can achieve in a system like that. So this was an example of discrete event simulation modeling in the area of aluminium rolling, in the area of an aluminium rolling mill plant. I have then also some other examples for the application of analytics. And this is an example related to container industry, also an example from my employer, Amova. And Amova is also member of Boxboy, or one of the joint venture partners behind the brand Boxboy. And what you see here in this video is a demonstration of a high bay storage system that is operated by stacker cranes for container handling and container storage in container terminals. And the video starts here by displaying a conveyor loop that runs below the high bay storage system. So you have self-driven pallets that drive here underneath the high bay storage system on, you could say, some kind of rail system. And once they reach the end, they are picked up by a pallet shifting car that then shifts over the pallets. And the pallets then drive to the other side and the end of the other side, and then they're shifted back again. So the pallets circulate and are self-driving. And the pallets are used to either receive containers from the high bay storage system or to send containers to the high bay storage system. You see here an animation of how the high bay storage is then built up above this conveyor line. So you have, of course, different kinds of columns. Some columns, they are for example, 40-foot containers. Some columns, they are for 20-foot containers. And usually you put the heavier containers, so the containers with heavy loads, at the bottom of this this rack system, and containers with a lower weight, try to place on the higher levels of this rack structure. The advantage of this system is that you can, using these stacker cranes that you can see here in purple, you can pick every specific container that you want directly. And this is a difference to conventional container yards, where you usually work with a block storage, and you store containers in a block storage. So you put containers here on the ground, and you stack containers on top of each other. And then in some cases, if you need a container from the bottom of the stack, you need to reshuffle the containers. And this, of course, takes time and means lower productivity. And this box-based system that you can see here in this video you can pick every container that you need directly without having to reshuffle other containers, and that supports a very high performance and a high throughput, and in the end also means that you can work faster and ship more material through your terminal in shorter time, and thereby also, of course, make more money. And the reason why I put this in this presentation is that this is also an area where we at MOVA develop simulation models, and is a highly complex system, highly complex material handling system with a lot of interactions between different kinds of equipment. You see here the stacker crane. The stacker crane interacts, as you saw, with the conveyor line running below the high-bay storage system. In some designs, you also have various or multiple stacker cranes in the same aisle. So stacker cranes have to interact with other stacker cranes. And then you saw also earlier in the video that pallets are then, or containers that are, for example, retrieved from the high-bay storage system, are picked by truck cranes that put the containers onto trucks. And also this interaction is a highly dynamic type of interaction and a very complex interaction. It is not easy to assess the throughput performance of a system like this. And with conventional static calculation approaches or engineering approaches, you would not be able to fully analyze the throughput capability of a system like that, and therefore we also in this area apply discrete event simulation modeling to basically develop a model of a system like this that describes the high-bay storage system and the equipment involved in a system like that, and using that model we then run various throughput scenarios to validate the throughput performance of a system like that. Essentially this means that analytics and simulation as a part of analytics is applied here to support very important decisions and to optimize design of, as you can see, very big and impressive logistics systems. As the last thing, I should note that what you saw here and what I did not mention is that the system is not only connected to trucks, but also to straddle carriers that can hand over or pick containers here from handover positions at the side of the high-bay storage system. And when conducting a simulation study, you would then also consider the material flow by truck and the material flow by straddle carriers, as well as the interaction with the key cranes that you see here. The system is no longer only an animation. So what I show you here is a video that's also available on YouTube. You see here the video starts again with the animation that we already saw. This was how it was originally designed. There are different concepts of this system. This is just one configuration, you could say, of the system, but you can also configure the system in different ways. I'm going to fast forward a little bit. I just want to show you that tests were then conducted, in this case with, you see a test of the telescopic unit of the stacker crane that's responsible for handling the containers in the high-bay storage system. So that was one of the steps when this system was then engineered and developed. And what this aimed at was developing a a proof of concept facility. So this proof of concept facility is the box by proof of concept facility that you see here. And this is from the early construction phase and video that shows you basically the early stage of the construction process. And as you can see here, this is where the conveyors would be running. This is now a rather a smaller a proof of concept facility with only or with two aisles where stacker cranes will be operating. And that was a very early video. By now, this proof of concept facility is fully operational. And so now we have a fully operational facility where we can test what was analyzed in the beginning. And so the simulation models, the discrete event simulation models, and all the analytics that was applied in the design stage is now being verified and tested in reality using this real system that is now being used for running, for example, throughput test runs and various kinds of performance test runs. Yeah, and this is also one of this kind of facilities. So you probably have not seen this type of facility anywhere else before. So that was an example I wanted to show, just to show how important analytics can be in the design stage. And in this case, this was an application of discrete event simulation modeling that was applied to the design of a high-bay storage system for container terminals. I have some other discrete event simulation examples since I'm a discrete event simulation engineer. This is an example of a packaging line that is connected with high-speed transfer cars to an automatic storage and retrieval system. You can see here there's a container, there's a conveyor system here that is connected to the automatic storage and retrieval system, and the transfer car system down here. And also this was a process where, or a project where a design was developed by a mover, and simulation was used to validate the performance of the automatic storage and retrieval system, and also the throughput of the conveyor system that you can see down here. This is a conveyor system where there's a lot of interaction between the in and output of the various aisles. And one of the questions here was whether some kind of bottleneck will be occurring here on the crossing tables in the middle section of the conveyor system. And to assess whether a bottleneck would be occurring in a system like that, a simulation model was developed. And using that simulation model, various scenarios were analyzed to then eventually validate the estimated throughput performance of the system. So also an application where conventional engineering approaches were exhausted, you could say, and discrete event simulation was used to validate a real-world logistics system. I have also other examples. This is an example of a flat bay storage system. In a flat bay, you store the material on the ground. And as you can see, in this case, we are talking about steel coils. So this is a flat bay storage system for a steel coil yard that is then connected to various processing lines. And also here with conventional mythology, you quickly reach a limit when, in terms of really accurately estimating the throughput performance of a system like that. Mainly also due to the interaction of the horizontal cranes that you see here. So also in this example, you have multiple horizontal cranes that interact in a yard. And these cranes, they need to interact with one another. They need to avoid one another. And these kinds of decisions and interactions, they are hard to catch with conventional engineering approaches. And this is why you want to develop a simulation model to assess the impact of these kinds of interactions. There are also other things that are complex in a system like that. For example, if you look at these coils here, they can be stacked on top of each other. And then, similar to a block storage in a container terminal, you have the problem of sometimes having to reshuffle or restack coils in the coil yard. And that, of course, has a high impact on the throughput of a system like that. And that is also something that can be investigated with a discrete event simulation model. I have one more example here. This is a pallet transport system for a steel coiled rolling mill plant. So here you have pallets that travel along a conveyor system, and this conveyor system is connected to various processing lines. Those these processes that are connected to the conveyor system are not animated here, so you cannot see an animation of the various lines connected to the conveyor line. But there's, for example, there are coilers here. So these steel coils that you see here are handed onto pallets at one of these coilers. This is why an empty pallet is waiting here and is then sent to a coiler to receive a coil. There's an inspection line here, and there are, for example, marking robots here in this area, as well as horizontal cranes in this area that then pick coils and put the coils into a container a coil yard. All of these processes were modeled in the logic of this model, but there's no animation that shows these processes, but they are considered in the model. So also here an example of a simulation model used to assess throughput and assess design of a logistics system. I also have some other examples. These are some examples from my blog. For example, an example here using TechGL, which is a visualization library that I think is also used by Uber, and that can be used, for example, in combination with Mapbox. TechGL allows you to create, for example, three-dimensional heat maps to visualize spatial distribution of your data. So if you, for example, think about customer demand, this might be a great tool or library to get into to visualize the spatial distribution of your demand. For example, let's say you want to build a new warehouse somewhere, or you want to build a new sales store somewhere. Then using a visualization of your sales data like this would allow your managers to decide where to put the focus and where to consider a greenfield project for a new warehouse. Or you could also maybe cluster your customers based on certain attributes and visualize it on a map. Also, this is possible with, for example, TechGL, and is also a good example of visualization and how analytics and visualization can be used for supply chain analysis, maybe especially in the strategic phase. This is an example of center of gravity analysis. So what you see here are longitude and latitude on the two axes of this plot, which are basically the coordinates of spatial data. And then you see customer demand visualized with red dots. The bigger the dots, the higher the customer demand. And then using a center of gravity approach, which basically searches the center of gravity of this demand, you can estimate an optimal location for your warehouse. So a very simple approach that searches for the center of gravity to assess a potential warehouse location and to propose an option for management where they might consider a greenfield project for a new warehouse, if that is the problem that you're working on. And finally, I also want to provide one more example from my blog related to agent-based simulation modeling. So what you see here is a simple agent-based model that consists of a grid. So this is nothing more than a matrix with 2 dimensions. So x-axis and y-axis could be some kind of abstract dimension that basically represents the world. And inside this world, you have here green and blue dots, which are basically your agents. And these agents are now interacting with each other. So each agent has some internal logic, some internal functions, and throughout the simulation, those agents, they interact with agents in their neighborhood. In this case, there's a battle going on, and what we want to investigate are 2 alternative types of survival strategies. We want to see which type of survival strategy is the most effective. So green agents, inside their logic, they have a different type of survival strategy, and then the blue agents. And then when simulation starts and the agents start to fight with other agents in their neighborhood, step by step, agents disappear from the battlefield, and in the end, you then have some kind of final state in your model where no changes are occurring anymore, and an equilibrium has been achieved. And then you could measure some kind of statistic to then assess in this simulation what was the best survival strategy. For example, you might say, okay, here steady state has been reached, and it seems that a survival strategy of type B agents is more successful. You can then also conduct sensitivity analysis. For example, you could adjust the initial population size of the various agent groups a little bit, and you can see whether this has a big impact on your results. So that might give you some kind of risk measure for the conclusions that you draw from this analysis. In this case, even with an adjusted population size, the type B agents are still more successful. And this is another example of sensitivity analysis where the range in which agents can attack one another is adjusted to see whether that has an impact on battle outcome and on the decision of which type of survival strategy is the best one. And you can see when this parameter is changed, so when the range or the radius within agents can attack other agents is adjusted, then both strategies perform poorly or the same, and there's no difference between the 2 strategies anymore. And so you can use this kind of modeling approach to ask all kinds of questions that you try to explain with interactions on the microscopic levels of a system, and you can use this kind of approach to derive some kind of conclusion on the impact of microscopic interactions onto the microscopic characteristics and trends of a system. So, for example, you could also model an economy using this approach, and you could address certain theories from economics using this approach, or you could try to forecast sales using this approach by modeling your market with agents. So definitely also a very interesting approach that I wanted to present here in this presentation. And I think that concludes the slides that I had for this meeting or for this event. And thank you very much for the attention.
Well, thank you very much, Lennart, for your very enriching presentations. Now I'm gonna start reading out loud the questions our public has written here in the chat. So I'm gonna start with, in your opinion, what is the fundamental base for industrial engineers?
Yeah, for me, it's a mixture of definitely mathematics. So mathematics, a strong mathematical foundation, as you would also find it in quantitative business degrees, and then maybe a small amount of computer science. So learning maybe one object-oriented programming language, like for example Java, would be an interesting component, in my opinion. And on top of that, of course, operational understanding. So introductions to operations management and foundations of operations management, supply chain management, as well as then process engineering and manufacturing engineering. So getting to know some technology for production that is important to your country or the economy of the country in which you want to work in.
Thank you. The next question, if you had to choose only 3 out of the 9 tools you mentioned that industrial engineers should know, what would they be and why?
So this was this slide, right? Yeah, definitely I would use still Excel, VBA, since or Excel in combination with VBA, and it's the most important tool, I think, in most companies, and that's therefore the first one you should master. And then personally I would choose Python, because it's a so important language in the area of data science, and there's so many modules available now for conducting analytics. For example, also many modules that allow you to develop mathematical optimization models for linear programming, non-linear programming, scheduling. I mentioned Google OR Tools is available in Python, and it's also a quickly growing language, and a lot of jobs require Python programming. And then for large data sets, for working with large data sets, I would say SQL. If you want to work in a manufacturing company and you want to work in operations, in planning, in operations planning, operations execution, then instead of SQL, I would definitely say SAP, not necessarily SAP ABAP, because that's only for developing applications, but SAP as the tool itself, is, at least in Germany, is definitely maybe then if you want to work in operations, the first tool I would learn.
Great, thank you. And any free of those tools that could be recommended for a beginner and that you can learn empirically?
Yeah, I mean, there are an SAP, which is not a program, like I said, it's an ERP system. So this is a software for managing operations and procedures in an enterprise, for example, logistics or manufacturing, but also purchasing, sales, HR. For SAP, I think there's a version online that you can buy through sites where you can websites where you can make an account, and then you can have like a monthly subscription model, and then you can use a version of SAP that allows you to develop a demo system of a company, and that allows you to train SAP, and that would maybe be a good idea for getting started with SAP, in combination with a book that you can purchase online, that provides an introduction to SAP. And if you're more into algorithm development and data science, maybe also mathematical modeling, then I would recommend Python, since I think Python is more beginner friendly than, for example, C++ or Java.
Thank you. The next question, do you think that if most of the international ports use this type of facilities, would it be helpful for their connectivity among ports?
Yeah, I mean, certainly. I mean, the advantage of this system is that you can, for example, load or discharge your vessel with a higher throughput performance. So you can have a higher productivity at the key cranes, and eventually your vessel can leave the terminal earlier, and thereby you can reduce the dwell time of a ship inside at the terminal, and therefore the ship arrives at its target destination or its next destination earlier than it would otherwise have, than what otherwise would have been the case. So I would say yes, it can improve the connectivity.
And the other question regarding the same topic, can you mention some countries that have already this systems of container?
Sorry, some what?
Can you mention some countries that are already using this type of systems?
No, so this system is a totally new system, and it was invented by Amova in collaboration with DP World, forming the joint venture Boxbay. And so far, the only real-world facility in use is the proof of concept facility that I also showed videos from. And that is the first time anyone has built a system like that in those dimensions. And now the goal is over the next 10 years to roll out this technology and to expand it into the world and to enter big container terminals.
Regarding project management of such high-tech projects, how long does the design phase take before the real implementation?
Yeah, it depends on the project, but and the complexity of the project, and also the various stakeholders that are connected to a project like that. So especially when we're talking about a big container terminal like that, then there are always some investors. There are always maybe some local for example, politicians, and there are many things that have to be considered. And in addition to that, there's of course the engineering in itself that is very complex. And so in general, I would say here we are talking more about several months or years, and not weeks. So these are more longer planning projects or design projects.
Okay. Another question regarding the project management. Do analytics take into consideration the carbon footprint or environmental impact for such big projects, like the ones you've been presenting?
Yeah, it is actually taken into account. Yeah, so for example, electricity consumption is something that can be taken into account if you, for example, develop a discrete event simulation model for a facility like the one I showed. So yes, in your simulation you can, for example, calculate the total electricity consumption, and thereby derive the carbon dioxide that would have been produced by those movements if you build the system in reality. And then you can compare different strategies, maybe different management strategies for the warehouse, so warehouse management strategies, to see which one improves the footprint, the environmental footprint. Maybe you can also compare different layouts to see which one uses less electricity over time. So yeah, you can definitely use this to address these kinds of questions too.
The next question, what are the key factors to consider when designing a distribution network?
Yeah, the market, the process in general, I would say there's depends on the project. Some projects in network design I would maybe related to a network that already exists. So here you maybe have a new warehouse you want to establish. Then you need to understand the existing warehouses and the existing distribution centers. You need to know exactly what capacity they have, what's the throughput capability, how many employees do they have, what's the cost structure, since you also need to develop cost models. Then you need to analyze the supplier network. You need to analyze the the customer side. So what does the demand network look like? Oh, can you hear me again?
Yeah, yes, we can hear you now.
Yeah, I was kicked out by the firewall. I'm sorry.
Oh, okay. It's okay.
Yeah, but I think I met my point that first step would probably be a situation analysis, understanding the existing network, and that is probably also in most cases the most important step. And then after that, you develop the model. So once you understood the network, you then can develop a mathematical model. And you would probably need mixed integer programming. And you need some kind of modeling system. For example, you can use Google OR tools. In Python, you could use GAMS as a modeling language. And once you have your model, you can then solve that using a solver, for example. Cplex is a famous solver. Kurobi is a famous solver. And yeah.
Great. We have a few more questions that are getting more specific into the topic, transport and logistics in Panama. But yeah, I'm still gonna ask them. So since this is a very advanced system to carry containers, pallets, and those types of merch, do you think that with this automated system, the number of scheduled shipped stopovers per week in a country could be reduced? What would be an average time period?
I have to hear the question again.
Sure. So since this is a very advanced system to carry containers, pallets, and those types of merch, do you think that with this automated system, the number of scheduled ship stopovers per week in a country could be reduced?
The number of ship stopovers. Stopovers. So I would maybe have to understand what a stopover is.
Sure.
So I maybe have a hard time answering that question. But in general, as I said, I mean, with higher throughput, takes less time to load a ship, and that's of course especially interesting for bigger ships. And the trend would support bigger ships, and with bigger ships, you would need maybe less ships, and thus also less stopovers, if I understand the term stopover correct.
Yeah, thank you. And well, the only questions were just based on your experience in countries such as Panama and their logistics. Would it be feasible to implement such systems in a country like Panama?
Yeah, I mean, the system can be implemented everywhere around the world, I would say. So definitely in Panama, it could be built a system like this. I'm not an engineer who is involved in the foundation work or the equipment development of this system. I'm focusing on the logic behind it and developing a simulation model for the layout that has then already been created by an engineer. But in general, this system can be developed everywhere, and where you would want to use it is where it has a competitive advantage. So, for example, you need less space, surface area, or you need to have a very high productivity rate. Where in terminals where this is important, this system would be of interest.
Well, thank you very much, Lennart, for your presentation today, which has been really enriching for our students. There have been many questions, and I think now they comprehend a little bit more the importance of the mathematical models that they use. So, well, I'm going to say also this in Spanish. I want to say thank you again, and I would like to ask you, Lennart, if you can stay 5 more minutes so we can have a small networking session with the professionals here and the professors. Just a small talk.
Yeah.
Muchísimas gracias a todos por su participación. Se ha visto que sus preguntas han sido muy interesantes y están muy emocionados con el tema. De verdad, estamos muy contentos de haberlos tenido a ustedes, estudiantes, profesores y profesionales. Le pido a los invitados profesionales ya graduados y a los profesores que se queden, profesora Videlia, Freddy, Rolando, Stephen, profesora Milva, por favor, quédense un momentito nada más para hacer un pequeño networking con nuestro conferencista, en caso de que tengan algún tipo de preguntas ya diferentes. Y por lo demás, bueno, les estaremos informando después a ustedes estudiantes en Instagram sobre nuestras próximas conferencias en mayo, 14 de mayo, también tendremos otra, pero ya tendrán futuramente información acerca de ello. Así que nuevamente, muchísimas gracias and well, thank you everyone. And see you in May for our third conference. Bye. Have a nice weekend, todo mundo.
Bye-bye.
Ja, so, ja, kannst hier gerne bleiben, ne, für ein paar Minuten.
Ja, danke.
Ich will das einfach nur hier starten. Also, ja, das sollte nicht hier bleiben.